Okay, so I'm going to try to record a little video just talking about examples of induction and Faraday's law and Lenz's law. Faraday's law says that the induced EMF in either a physical loop of wire or a circular region of space is equal to the negative of the rate of change of the magnetic flux through that loop. And that negative sign you can really think of as being Lenz's law. Lenz's law is that the direction of the induced EMF always opposes the change of magnetic flux. I just wanted to show a couple of video examples of situations where we see the effects of magnetic induction. And one is just this YouTube video. I'll just keep the sound off and I'll provide a narration for the video myself. You've got a copper pipe, and the first thing we show is just that there's nothing weird going on with the pipe by just dropping a metal ball through it. The metal ball falls through, accelerates downward the way you'd expect a metal ball to fall through in about a 2/10 or 2/100ths of a second. But when you drop a magnet through the tube, it takes much longer for that magnet to fall through. This isn't a video trick. This is actually what happens if you drop a magnet through a copper pipe. What's going on there? Rather than let the YouTube video explain what's going on there, let me explain what's going on there. Copper is a conductor, which means in the metal, electrons are free to move around in the pipe. If you drop a magnet, say with the North Pole facing downward through that pipe, and you imagine an imaginary line through space inside that copper, when the magnetic flux through that region of space changes, that's going to create a induced EMF. That's going to create a current pushing those electrons around that loop, and that current is going to induce its own magnetic field. And Lenz's law says that that magnetic field will oppose the change in flux, which means there will be a force that opposes the motion of that magnet through the field. So the magnet will fall more slowly. It will feel a resisting force as it tries to pass through that pipe. Another video that shows this really nicely is this video showing, let me see if I can cue it up to the right spot, a magnet swinging towards a large piece of copper. So only one of these objects, the object on the string, is the magnet. The other object is just a big chunk of copper. And what you see is that as the magnet approaches the copper, it stops abruptly in that induced magnetic field. The copper itself is not magnetic. When it's stationary, it doesn't induce a magnetic force. But when the object tries to move through that magnetic field, there is a induced currents caused by the induced EMF. And if this is your block of copper and this is your magnet, again, let's imagine that, say, a north pole of the magnet were moving towards this copper. That changing magnetic flux will create what's sometimes referred to as eddy currents. In other words, if you know the word an eddy is like a small, if you're looking at water flowing, eddies are these little swirls of water around rocks and stuff in a stream. Eddy currents within a metal are small currents at the microscopic scale of free electrons that are able to flow around in circles, each of those creating their own little magnetic field. And again, because Lenz's law says the direction of those magnetic fields opposes the change in flux, the directions of those induced magnetic fields by those little tiny microscopic currents in the copper will create a force that opposes the flux and a magnetic force that opposes the motion of that magnet. We haven't talked about alternating current yet in our discussion of circuits, actually. That's the last thing we'll do with some videos on Monday if we have the chance. But you probably know that the current in our house is not like the current from a battery that just flows from positive to negative. The current actually fluctuates over time from the positive direction to the negative direction sinusoidally. So the current equals some maximum current times, say, sine of omega t, which means that if you plug a wire into an outlet in your house, the current isn't just flowing in one direction, it's flowing in one direction, then the other direction, then the other direction, the other direction, back and forth. That means the current is constantly changing. It means that any magnetic field created by that current will also be constantly changing, and this leads to a couple of situations where you can use this changing current and the magnetism induced by that changing current for beneficial effects. One example where induction is used for something useful is inductive heating. If you've got a coil of wire with alternating current flowing through it in one direction, then the other, then the other, then the other, that's going to create a magnetic field that points first in one direction, then the other direction, then the other direction, other direction. That loop of wire creates a magnetic field. The current is constantly changing. The magnetic field is constantly changing from up to down to up to down. If you put something on that object that is made of a conductive material like copper, the magnetic fields pointing in one direction and then the other direction, then the other direction will create eddy currents that will create little magnetic fields of their own. And when you create a current in a metal that has resistance, that energy is dissipated somewhere, and that energy is dissipated as heat. And this metal will actually get hot. And if you've ever heard of an induction cooktop or inductive heating, okay, there are stoves that you can buy for your house that will heat up a copper pot that you place on the stove, but will not heat up, for example, your hand if you put it on the stove, because the cooktop isn't getting hot. What the cooktop is doing is creating a changing magnetic field that creates eddy currents and causes resistive heating inside certain metals. Another example where this can be used is to, if you've got, say, a coil of wire with a certain number of turns and a current that's flowing through it first in one direction then the other, and you place that coil of wire next to a second coil of wire with, say, a different number of turns, this magnetic field points one way, then the other way, then one way, then the other way. That's going to induce a current in this coil that points one way, and then the other way, then the other way, and that's going to make a current flow in this coil of wire. If you have, say, more coils in this side of this device and fewer coils in this side of the device, the induced EMF in this side will be less than the EMF generated through this coil. So whatever voltage you measure on this side of the loop will be less than the voltage, the maximum and minimum voltage on this side of the loop. So the voltage over here is oscillating sinusoidally. The voltage over here will also vary sinusoidally. And the amount of voltage on this side, the ratio of this voltage to this voltage, is equal to the ratio of the number of turns in this loop to the number of turns in this loop. This kind of device is called a transformer. A transformer is able to change the voltage in into some different voltage out, and the way this is typically performed in an AC current is by using magnetic fields in the process of induction. The reason most electronic devices that you'll find in your house, if they're small, still have some kind of large device that lives outside of the appliance is because this device has a transformer in it. It plugs into the wall. The voltage in the wall in the US is 120 volts AC. But your computer doesn't want 120 volts. Sensitive electronics cannot run on a voltage of 120 volts. It wants something like 9 volts or 12 volts or 15 volts. So this transformer, this is called a step-down transformer, decreases the voltage from 120 volts at the wall to 9 volts or 12 volts or 15 volts, or whatever your computer is built to handle on the other side. One of the things that you notice about these is that they get really hot. Okay? They get warm. That heat comes from the resistive heating from the electrical current flowing through the coils inside of this transformer. Usually the way a transformer like this works is there'll be, at least in the olden days, it used to be usually a U-shaped piece of metal, like iron, that will guide the magnetic field lines from one coil to the other. There's one coil of wire on this side called the primary, where the voltage goes in, and the current goes in, and there's another coil of wire here called the secondary, where the voltage and the current come out. And if N of the primary is greater than the N of the secondary, it'll step down the voltage. If N of the secondary is greater than N of the primary, it will step up the voltage. So we have step-up transformers and step-down transformers. Usually in your house, you're stepping things down from 120 volts, say, at the wall to usually 9 or 12 or 15 volts at the device. And all of this changing magnetic field inside this metal core of the transformer, all of that energy that goes in is transformed into heat. And so these transformers tend to get warm as they work over time. The other interesting thing to notice about a transformer is these two halves are not electrically connected to one another. No current flows from here to here. This side of the transformer creates a magnetic field. Those magnetic field lines pass through the material, first in one direction, then the other direction. That induces a current in the other coil. That creates a current on the other side of the transformer. What that means is if I take the end of this that's going to my MacBook and I unplug it from the MacBook so that no electricity is flowing through that system, the electricity is still flowing through the primary coil of the conductor, which means that every device in your house that has one of these, whether it's inside the device and a larger device, the device is big enough, like a television or a microwave, the transformer is actually inside the device, not outside, like in a laptop. Current is still flowing through the primary all the time, even when the device is off, meaning that if you pick up a transformer in your house and it's warm, that's because electricity is flowing through that, meaning that device is using electricity, a little bit of electricity, all the time, even when it's not running. You sometimes see these things referred to as power vampires, meaning that even though they're dead, the device is not on, the transformer is still using electricity. So there's some people that advocate for putting all your devices on a power strip and turning that power strip off when you're not using the devices so that all the transformers connected to all those individual devices are always turned off and not using a little bit of electricity all the time. So we talked about inductive heating. We talked about transformers. Oh, the other thing to talk about is this is something that's just become common in recent years, the idea of an inductive charger. If you've got alternating current flowing through a loop of wire, creating a magnetic field that goes in one direction and then another direction, you can take a device that has got a similar loop of wire inside, connected to a battery, and you can, without having these two devices touching, have the magnetic field, the alternating magnetic field, being created by this loop with a changing current in it, passing through this loop in the device, inducing a current and an EMF in that loop and charge that battery. That's how wireless chargers work. Okay, sometimes called inductive charging. Okay, many of you might have phones or other devices that charge wirelessly, and that's taking advantage of the induction created by the magnetic field in a loop with an alternating current, creating a changing magnetic field through another loop. That creates an induced EMF, that creates a current, that can charge your battery. One last thing I want to talk about before next week is, well, let's just imagine the situation. Imagine you've got a coil of wire. Okay, a solenoid, okay, just a coil of wire wrapped around some horizontal axis. And you connect that to a battery. And you connect that to a switch. Imagine the battery is disconnected. Nothing's happening. No current's flowing. There's no magnetic field. Imagine the switch is closed and the current is flowing. While the current is flowing at a constant rate, this creates a magnetic field. The way I've got it drawn, the current goes around this way, so the magnetic field will point in this direction inside the solenoid. Right hand rule, wrap your fingers around the direction of the current. Your thumb points in the direction of B. But when the current is flowing at a constant rate, the magnetic field is constant. Constant magnetic fields don't cause any induced EMF or induced current, so everything is just fine. But imagine the moment when you just turn this current on. The current is going from I equals 0 to I equals something that's not 0, which means the current is changing. The changing current means that the magnetic field will also be changing. That means that if we take one of these loops of the solenoid, of the loop of wire, the magnetic flux through that loop will be changing as well. It will be something non-zero. So a loop of wire, when the current is changing, creates a changing magnetic field. And we know that changing magnetic fields create EMFs, create a voltage, create an induced current. And we know from Lenz's law that the minus sign in Faraday's law means that that induced EMF always opposes that change in the magnetic field, meaning that the induced magnetic field in the loop and then the induced EMF in the loop will be in the opposite direction of the magnetic field of the loop and the EMF being applied to the circuit. That means that a loop of wire like this will inherently resist changes in the current. That phenomenon is called self-induction. And that object, that circuit element that resists changes in an electrical current is called an inductor. Okay? An inductor resists changes in current. When the current is flowing at a steady rate, inductors don't do anything. They've got a little bit of resistance because they're made of wire, but inductors only function in an electrical circuit to resist changes in that current. So we've got a new circuit element. We've talked about resistors. They have a property called resistance, and what they resist is current. Now we have these things called inductors. We draw inductors as little loops. They have a property called inductance, for which we use the symbol L. Why? Because I already stands for current, and there's only so many letters for things to stand for, so I'll use the symbol L for inductors, and they resist changes in current. Okay? Inductance, this quantity, is measured in units of henries. You know what? I don't even know what Henry this is named after. But the unit of inductance is the Henry. And we'll talk about what that is in SI units, and we'll see how to use inductors as elements of circuits next week. So we won't do many examples of inductors by themselves. Where things get interesting is if you've got a circuit that has got, say, a resistor in it and an inductor in it and a battery and, let's say, a switch. Okay. What will happen to the current if I measure the current through this, say I put an ammeter here and measure the current through this circuit over time? If the inductor wasn't there, the current would just be whatever the current is. It would just use Ohm's law, V equals IR. You find the resistance, you know the voltage, you calculate the resulting current. But when you close this switch, this inductor will create an induced magnetic field and an induced EMF that opposes that change in current. It will fight against your effort to get the current to achieve this maximum. So the current will do something like this. It will gradually approach that steady state over time. And the greater the inductance is, the longer it will take for it to reach that ideal value, I equals the voltage of the battery over R. Okay. So we have a situation where we've got a quantity, the current. We've got the inductance, which affects the rate that the current changes over time. And we can see that in order to write an equation for what happens in a circuit like this, we're going to have to solve a differential equation that involves both the current and the rate of change of the current. So what we're going to look at next week are circuits that have resistors and capacitors, circuits that have resistors and inductors, or inductors and capacitors, and circuits that have resistors, inductors, and capacitors all together. And we're going to see that the differential equations that describe these various types of circuits actually look kind of familiar to differential equations. They look similar to differential equations that we solved way back in first semester in our mechanics unit. So I'll give you a couple of sample problems, maybe Friday, or I'll post them over the weekend, about inductors. But the only reason I'm talking about inductors is so that we can get to RLC circuits and get to this differential equation, which is super, super, super important. One last thing, I might switch over to these YouTube videos. I've been showing them here with the narration turned off. It would be a great exam question to give you a video clip of something like this. Let me get it like this. A video clip of a magnet swinging towards a piece of copper and ask you to draw the situation, to draw the directions of the magnetic fields, and to explain what happens in terms of Faraday's and Lenz's law. Actually, what would have been a great sort of final project video would be to give you this video, just cut out the demonstration part where he drops the magnet through the pipe, and ask you to record your own narration. to record your own 30-second or 60-second narration explaining what happens in this video. Why can't I go back far enough? Here we go. Okay. Explain what happens in this video in terms of Lenz's law, Faraday's law, induced currents, magnetism, and so on and so forth. So something like that would make a great exam question to sketch the situation, to explain what direction the magnetic field is, what direction the magnetic flux is, and so on. Okay, so I will leave that at that. I will post this video. You can watch it over between now and Thursday, and then we'll talk about inductors, RLC circuits, and this differential equation for the current flow through a circuit that has elements that resist both the flow of charge and the rate of change of the flow of charge. Yeah, and then I think what I'll do is after we do that, I'm going to record one sort of bonus video on Maxwell's equations, and then we will be done.